Alright, so in our previous video we talked about what electronegativity is, how it changes as you go across the periodic table and as you go down the periodic table. And now we're going to talk about how do we apply that into chemistry, okay? So we know that fluorine is the most electronegative element. And we also know that as two atoms get close to each other, there's this, all that's going on is there's a lot of repulsion amongst the electrons, but there's also attraction between the nuclei of both of the atoms as those electrons approach each other. So there is some repulsion and there is some attraction that occurs between, again, the electrons and the protons of the electrons of different elements, okay? So when we talk about a bond and we talk about how strong that attraction is, we know that that deals, again, with electronegativity, okay? So when, I think we used this example in the previous video, for example, fluorine, okay? In the case of fluorine, this bond right here is not being, the electrons in that bond are not being pulled closer to one fluorine than the other. Because their electronegativities are equal to each other, that bond, those electrons are shared equally. So in that bond right there, the electrons are shared equally between both atoms, okay? But anytime the atoms are different, such as in HF, for example, because fluorine is more electronegative, the electrons, again, in this bond, the electrons are not shared equally, okay? And what that does is it creates different types of bonds. We know that in both cases, both those fluorines are obviously nonmetals, and hydrogen and fluorine are both nonmetals. In both cases, they're both covalent bonds, okay? Because, remember, covalent bonds are between two or more nonmetals. So they're both covalent. But there is, within the covalent bond, there's two different types of bonds. There's ones where, again, the electrons are shared equally, and ones where the electrons are not shared equally, okay? So when two of the same, so that's our case here, two of the same nonmetal atoms form a covalent bond, each atom pulls on the electrons in the bond with the same attractive force because, again, they have the same electronegativity. This type of bond is called a nonpolar bond, okay? So here, where these electrons are shared equally, it is non-polar, okay? When two different nonmetal atoms form a covalent bond, most likely one of them will have a greater electronegativity than the other, okay? And when that happens, the electrons are not shared equally. One atom is pulling stronger on those electrons, okay? And that creates what's called a polar bond. So in this case, that is a polar bond because, again, fluorine is more electronegative than hydrogen is, okay? And there's even ways that we can represent that. If we want to show that where those electrons aren't being shared equally, we want to show that the electrons are being pulled more in the direction of the fluorine. And the way that we do that is we kind of make a little plus sign, but then we keep that part going and we make an arrow pointing in that direction. And the reason for that is that shows two things. It kind of shows, again, you can kind of see it's a positive sign right there. Because those electrons are more attracted to the fluorine, it does produce a partial positive charge on that hydrogen ion. Remember, if something loses an electron, it has a positive charge. So even though hydrogen hasn't lost the electron, because fluorine is so much more electronegative than hydrogen is, we call it a partial positive charge, okay? And then obviously the arrow is showing the direction in which those electrons are attracted. So they're more attracted to the fluorine side, okay? And what this little arrow thing is called is this is called a bond dipole, okay? So anytime you have a polar bond, you have a dipole, okay? If it's a non-polar bond, remember, there is no dipole. There is nothing pulling the electrons in one direction more than another. So only in polar bonds do you have what are called these dipoles, okay? So in example 1 here, we just talked about it. The bond in F2 is nonpolar, but in HF, it is polar. Okay, explain. Okay, so why? So in F2, okay, because fluorine has the same electronegativity, the electrons are shared equally. Okay? And like we just said, there is no dipole. Okay? But in HF, because fluorine is more electronegative, the electrons in the bond are more attracted to F, creating a dipole. Okay, creating this right here. Okay, so a nonpolar bond is one where the electrons, again, are being pulled with the same amount of attractive force by both atoms. Okay, likewise, a polar bond, so the opposite, is one where the electrons in a bond are being attracted or pulled more towards one atom than another due to that difference in electronegativity. Okay, so we've got polar bonds and we've got nonpolar bonds. Okay, something like CO. Okay, absolutely, that bond, even though it's a triple bond, it doesn't matter. That bond is absolutely polar. Why? Because oxygen is more electronegative than carbon. And so the electrons in the bond are more attracted to the oxygen side, creating this, again, this dipole. Okay? I'm trying to think of another example here. In PCl, okay, in that molecule right there, okay, we've got this. I'm just doing the steps of the Lewis electron dot diagram. 2, 4, 6, 8, 10, 12. So in that molecule right there, there's a double bond. Again, that is a polar, this bond right here is a polar bond because chlorine is more electronegative than phosphorus is. So again, we've got a dipole going this way. Okay, and really, anytime those atoms are different, under very rare circumstances do you have two atoms that have the exact same electronegativity. I want to say one of our previous videos, I want to say hydrogen and phosphorus have the exact same electronegativity. But again, that's very, very rare. Okay, anytime you have two different atoms, one of those atoms is going to be more electronegative than the other in general, and so you're going to have a polar bond. Okay, here's the problem though. You look at every example that we've done so far: two atoms, two atoms, two atoms, two atoms. Of course, most molecules have way more than just two atoms in them. Okay, so polarity can also be related not just to the bond, but to the entire molecule as well. Is the whole molecule polar or not? Okay, for example, a molecule can actually have polar bonds, but overall it can be non-polar. Okay, but it can also have polar bonds and also be polar overall. So what determines whether the whole molecule is polar or not, not just the bond? It depends on what's called the geometric shape of the molecule. Okay, and that will be our next video, will be a video about shapes of molecules, and then we're going to come back to polarity and talk about how does the shape of the molecule determine whether it's polar or non-polar.